Alrighty then. Where should we start? How about we start right here, because I already wrote it up on the board and Thad corrected me that I totally had the wrong notation. Thank you, Thad. But just real quick talk about constants to highlight a particular point that I think may be of interest to a lot of folks within the community and just pretty much everyone in general. So we have constants of nature. Why are they there? Don't know. I'm trying to figure it out. But within the system here at the monastery that we're using for characterizing the dimensions of our realm of persistence, we come down to 5. And from those 5, we can use as our dimensional ingredients to create the recipes for the constants of nature that we have on the board back there. So we have 5, the Planck time, Planck length, Planck charge, Planck mass, and Planck temperature. Notation: small tp, L sub p, Q sub p, M sub p, big T sub p. That's what we're using right now. Okay, and when you look at these things, you notice, like Bobby, you were pointing out a little bit before, there are some very interesting features that go on here. Pretty much everything here has h bar, Planck's reduced constant, in it, as well as a factor of the speed of light. And with the exception of the Planck charge here, they also have big G, the Newtonian gravitational constant. And one of the first things that I noticed when I was initially kind of starting to play around with these things is, you notice, Planck time, a limit for time, as far as we know. And that happens to have the speed of light to the 5th. Well, that's pretty cool. And when we go down to the other boundary, the Planck temperature, the limit of temperature in and of itself to our knowledge, we also have C5, but there's an inversion there because these are all square roots or some variation of a square root. We have 2 in there for the charge. But you notice C5, speed of light to the 5th, goes from the denominator to the numerator. Oh, that's pretty interesting right there. The other thing you kind of notice is as you go through these, we have speed of light to the 5th, the Planck time, and then we have the exact same construction for the Planck length, except it's speed of light to the 3rd power. Well, that's very interesting, and you're like, oh, the heck can that be? This is time, this is length, but remember these are also square roots as well. And you got big G and you got H bar, so you got dimensions of mass and everything in there too. Then we get down to the Planck charge. And the Planck charge is interesting because it's actually broken up into pieces, which, well, if you're thinking about charge, something related to electromagnetism, that kind of makes sense. Because the electric field and magnetic field they're always perpendicular, always 90 degrees. Does this have something to do with it? I don't know. But it's broken up into the square root of pi times 2 times the square root of the speed of light, and E naught is the electric constant, times h bar again. So again, this is the only time we see E naught within these dimensions. G is within all of these except the Planck charge, and then when we'll get here in a second. But you have these different pieces, and initially I thought that was just like, I thought it was actually the, no, I'm thinking something else. Never mind. But we get down to the Planck mass. Planck mass is very simple. Speed of light, h bar, divided by big G. All right, we got the square root of that. Don't need any other powers. We just have this dimensional arrangement, and out pops the Planck mass. The Planck temperature, we've got to include a dimension of temperature. So how do we get that? Boltzmann's constant, right there. So we got Boltzmann's constant. We square that, and then the only dimension that will finally be kicked out after you finish computing all this is temperature. It's a really big number. So what the heck is the point of all this? Aside from being slightly amused that, oh look, speed of light to the 5th, boundary, speed of light to the 5th, boundary. That's cool. But within constants of nature, classically, or at least within a Newtonian dynamic, for about the first 7 orders of magnitude, classical stuff works really, really well. Once you start getting past that, once you start getting past 10 to the 7, 10 to the 8, once you start getting around the angstrom level, which is, I think, was it 10 to the negative 10 or 10 to 15? Somewhere in that atomic range there. We need to use other techniques that seem to get the numbers that we are measuring to the best of our knowledge. And one might wonder why this might be. I know I didn't. I didn't even think about it until Thad had mentioned it to me. Because if you look on CODATA, and you look at the constants of nature, you're going to probably find a pattern, something along the lines of extraordinary accuracy up to about the first 7 significant digits. And then occasionally different things happen. Like I know, was it Planck's constant, Planck's reduced constant? I think originally 2018, I think they had it out to about 12 significant digits and had fairly large error bars. And then when they had done the update, they literally just lopped it off at 10 digits. We have high confidence up to 10 significant digits, so you don't need to worry about those pesky error bars. Error bars do matter, so that was perhaps a smart thing to do. But one of the things you might think of is when you get something like, let's say, C, you got the speed of light in a vacuum, because we always got to say that. Vacuum. Okay. So if we got that, you're like, what is that? Speed. What's length divided by time? A unit of length per unit of time. So we should just be able to do, all right, so LP divided by TP, and we should get C, but not quite. It ends up being approximately C. Why? The interesting thing is when you go through and you put these constants in that we have great confidence up to about 7 significant digits. After that, you kind of start seeing some deviation there. Because if we go to Wolfram Alpha or CODATA or something, we have high confidence for the Planck constants for approximately, for most of them, to about 5 digits. So, for example, the Planck time, we got that, at least on Wolfram Alpha, it gives you 4, so we'll give you 5.391, and then times 10 to the 44th power. Oh, excuse me, negative 44. There we go. That was an 88 order of magnitude error there, so I've learned to catch myself. Usually it was because I was doing a computation. I'm like, why am I up by 76 orders of magnitude? Oh, I used Planck temperature. That's 10 to the 32. This is 10 to the negative 44. That's the 76 error. Order of magnitude error. Okay, so we got that. Okay, so that's a unit of time. So we'll just do this method because I did not think about space on the board. And then we have 1.163, 1.163, and that's 1. Ooh, chicken's done.
At least I have chicken.
That means I got to speed up. But, and that's 1 times 10 to the negative 35 meters. And when you do that computation, it comes out to be, basically this ends up equaling all to 2.9981451 times 10 to the 8 meters per second. All right, when I say the speed of light, I typically rattle off 2.998 times 10 to the 8 meters per second.
The speed of light is approximately 2.998 times 10 to the 8 meters per second.
I rattle that off wrong. It's pretty darn close. But when you actually compute C, the value of C actually equals 2.99792.458 times 10 to the 8 meters per second. Okay, it's only off by like 22,000 meters per second, but it's off. And that's what happens if you have to pad these out by adding some zeros on. So you had like 5 zeros on there and 4 zeros on there. So you could get it out so many digits on Wolfram Alpha. That's something you choose to. It's like, wait a second. But the speed of light is defined as the minimum unit of length per unit of time. What the heck's going on here? Now again, you could say, because this is one of the things that got me, it's like, well, if we know the speed of light to 9 significant digits, we've measured it. I realize we measure it in a fairly obtuse fashion, not directly, but we have a high confidence in the speed of light to 9 significant digits. Shouldn't we be able to figure out what the Planck time and Planck length are to at least 9 significant digits? Or 8? Why is it like 4 and 5? You might see them to 7, but those last 2 have like pretty decent error bars there. What's happening? Now, utilizing the method that Thad's developed here, we do have an answer because we have some closed forms. We have a poster over here. I'll add it up on the graphic as well as attach the computational notebook to this quick talk. And what it is we can do the speed of light. We can get it out to this. How do we do this? We do it by, we can have R C equal, like we were just saying, so the Planck length over the Planck time. And then that's our primary action. So we have an external, a primary action, times our boundary conditions. In this case, the primary action is just 1. We don't always see that. We have our dimensional ingredients here. And then we have our inner action here. That's 1 plus square root, because we love square roots, G, I. Oh, that's the square root of the Giesecke constant. That's nifty, because we take 2 Giesecke manifolds and merge them together, we can get the hyperbolic figure 8 knot. Seems really useful. And then that's times J1 minus J2. And then we have our inversion boundary over here, that box, Planck length times Planck length times Planck mass, all over Planck charge squared. Okay, and this guy ends up equaling out to 2.9979. 2, 4, 5, 8, 0, 9, and it keeps going. So basically, looks like the same number. That's times 10 to the 8 meters per second. So aside from my messy handwriting, you'll have the notebook. You can verify there. It's a process that seems to work. And one main reason I want to talk about this today is something that I've kind of heard is, I've heard that as we go to update different things and we go to adjust different constants, one of the things I learned from that is some of the constants we saw upwards of about a 3.5 sigma swing. And it can be really hard because you have all these different smart folks from all these different fields, and they're working really hard and they're trying to get the best estimates that they can. But a lot of folks there spend all their time in their field. They spend all their time working on their things that are important to them because they are important. The only issue that can run into is if you might have the best calculation that you have to your knowledge and the limits of our technology within your field. However, if you're trying to align everything up, like, what was that? I think we were on Wolfram Alpha earlier, and we took a look at the atomic mass unit. They have the atomic mass unit, but depending on which one you click on, like, okay, the physics one, okay, it's good for about the first 4 or so significant digits. And then you have the chemistry one, and then it's good for the, and you go through and it's like, well, these are different. These don't seem to be quite as unified as, at least I would personally hope. And again, I'm not a professionally trained physicist. I'm just a guy that's trying to figure out things that's been very blessed in my life. Now, what we're looking for is, the whole point of the metric system is to have a coherent system of units. And that's one of the reasons why we've chosen to use this system for modeling the physical world, to maintain coherence. And one of the really cool things, and this is something that I've still been trying to wrap my head around, and it just seems to almost make the mind wobble, is that Thad managed to find some solutions for these things, and the solutions are very interesting. And I think it's at least worth sharing, because it might help some folks. And again, I'm not going to say it's right or anything, but it provides maybe a clue for other smart folks out there to try to figure out what's going on, or maybe just even help them with some calculations. Give it a try. Hey, if it doesn't work and it ain't your thing, no worries. You don't got to use it. Just something that we're putting out there just so the world can try to, I would say level up, but I'm wearing the other shirt right now. But, okay, so one of the solutions here for, I like how you put them in the book, for the atomic mass constant. So it could also known as the atomic mass unit, the AMU, or sometimes the Dalton, depending on context. Okay, and we can write the A mass. So we'll do A mass, because I am from Massachusetts. And it actually has, maybe not all that surprising, actually similar construction to what we have for our Planck units there. And we can phrase that as 18 over 32, and then multiplied by pop, our universal parabolic constants, and then that's over J1 to the 6th power. So this is our primary action. Our boundary condition is the mass of the electron. That's pretty cool. That seems to be a very elementary unit, that basing it off something off of probably not a bad idea. And we have our internal action, which is just 1 plus 1 over the lemniscate, and that's just multiplied by J1 minus J2, and then we multiply just by our inversion boundary box there. Okay, so yeah, you just search for something like that. I mean, it's kind of neat. We're saying that we're working in a theory utilizing derangements, so the ways you can arrange different things. 18 happens to correspond with the charge boundary, 32 with the temperature boundary. Okay, that's kind of neat. And then you look at the solution that had found for the kilogram. I thought it was pretty interesting. So if we just do kg, we can set that equal to, again, similar setup. This is 32 over 18 J1 to the 6 over the universal parabolic constant there. And then I think it should only be kilograms, Thad, just because they're adding it to it in there. And when you do a computational, you know, it's going to kids. But you basically you can do 1 over the mass of the electron. In this case, if you want to balance out dimensions, because they're looking for the ratio of like the kilogram in AMUs, it would be actually the unit of the kg. All right, so we'll do kilogram. Yes, we're putting the kilogram in the kilogram. I realize it's a little ironic, but over the mass of the electron. And then you do 1 minus 1 over the lemniscate, J1 minus J2, times our inversion boundary right there. Make that a little less abysmal. Okay. All right. So what the heck just happened?
Kilogram on the left hand side, just one. And the mass is what?
It's the atomic mass unit. This is in ratio. We're utilizing the mass of the electron, which I'll put in the calculated notebook attached to the video. We're using the mass of the electron as our boundary condition. So this is our primary action, our boundary condition, and this is our inner, or we had called it the terminal action here, and it's the inversion over here. When you look, it's kind of just it is an inversion. It's like, all right, we put the 18 on the bottom, the 32 on top, we put the Joe 1 to the 6 from the bottom onto the top, and the universal parabolic constant from the top to the bottom. And then basically we just did 1 over the electron. We did this for computational purposes to cancel out the dimensions. And then you just go from 1 plus to 1 minus, same action. I'm not an expert, but there seems to be some symmetry going on there. But that's up for you all to decide for yourselves. I can't convince you of anything. I'm just sharing stuff that I found interesting. And when you look at the sigma on this, I believe it's 0. The sigma on this, if you actually go out with a few more digits, it's like 0.023% or 3% or something like that. And I'm like, I heard some folks saying that maybe something was it seemed a little off when they redefined the AMU and the kilogram with some of the updates. I have no idea what's going on. I can't verify it at all. I know there's a little note in like the Wikipedia article saying some folks disagree because it used to be just based upon carbon 12, 1/12 of carbon 12. Boom, there we go. But this is very interesting because if this is true, which we're going to have to see, this would imply there's very direct symmetry between the atomic mass unit and the kilogram, and it almost may help to explain why powers of 10 works so really dang well. And when you verify, this is verified, at least according to Wolfram Alpha, only deviation with what Wolfram Alpha has is in like the 14th significant digit and goes from like 9999 to like an 8 or something like that. So there's some deviation, full disclosure, whatever the reason for that deviation might be. I guess we're going to have to wait, see, and learn some more and do some more experiments. But that's all I really had for a quick little rundown of some of the constants. Yes, sir?
So the atomic mass number is 1.6 something. I looked it up just now.
Yeah.
The kilogram is just 1.
The kilogram in relation to the kilogram. Because the kilogram is 1, because the original way that had this was 1 over the mass of the electron to get out the dimensions of kilograms, because the mass of the electron we express in kilograms. But this is actually a relationship. This is kg in, they express it U, which is basically just the atomic mass unit or the Dalton. Because I just tried it as that, and you won't get that. In order to actually get the actual numbers to compute, you need to have it expressed as kg times the atomic mass unit in there. So that's its reference.
The digits are 1. The digit is not 1.
No.
It's a number.
Yeah, it's a number.
Yes, because the kilogram reference, that's why the quick hack, so to speak, is if you need to adjust the dimensions, they're just kilogram, meter, or something, because those are our reference ones for the system.
Yeah, it's a bit confusing because they use kg for the symbol of the constant, but the
So it's
full
not
thing is
kilogram, it's
kg.
kg.
It's kg in use.
Yes, kg expressed in this particular unit. And then when you multiply it, that's how you end up seeing the inversion here, because it ends up being a translation between the two of them, which, I mean, the first time I saw it, I'm like, wait, does this mean 10 is built into reality? No, that can't be the case. That can't be the case. It kind of looks like it may be the case. I don't know. But other than that, it's just very fascinating that you can utilize some algebraic geometry like this, and you can get a what looks like a pretty,
Serious symmetry.
yeah, some real serious symmetry going on there with the atomic mass unit and the kilogram. Also, when we utilize, the atomic mass unit as our boundary condition, I think in like the proton, the neutron, it actually helps simplify things a lot. So, is it built into reality? Well, if we think we're real, this seems to be part of reality, or at least a mathematical, pretty good approximation, I would say. Anything else? Alex? Bad. Good? All right. Chicken time then. Cool. Thank you.
Thank you very much.
See the past through a flashback, back to the days when I didn't have rap, but nowadays, bitch, I'm all about